In the last video, we introduced the idea of Lewis structures and saw the process by which we can go through and represent all of the bonding and non-bonding electrons in a compound to figure out how all of the atoms are connected and where all of our valence electrons lie. So in this video, we're going to address a couple what-if situations that you might come across and how that affects your process. So the first one is relatively simple. Yesterday we were dealing with just the structures of neutrally charged molecules. So to figure out the number of valence electrons in our structure, we just needed to go to the periodic table, find the group number of all of the elements involved, and add those up. So if you're drawing the structure for something that is not neutrally charged, of some kind of ion, the only thing that's going to change about your process is that it affects the number of valence electrons in the structure. So when you're doing that very first step of determining how many electrons do I need to represent in this structure, you need to make sure you account for that charge. So in cations, each positive charge means an electron is missing. So each positive charge removes one electron from whatever it otherwise would be. So if you have something with a +1 charge versus neutral, you can figure out the number of valence electrons for the neutral version exactly the same way as we always would, and then just subtract 1 for that +1 charge. If you have a +2 charge, it's going to be 2 fewer, so on and so forth. For anions, we have the opposite situation. Anions being negatively charged means there are extra electrons. Electrons are negatively charged, so if the thing is negative overall, it's got some extras. So each negative charge adds an electron. So that's just something to keep in mind if you're dealing with drawing the structure of an ion, to make sure you adjust that number of valence electrons correctly. Remember, if you don't end up with the right number of electrons in the structure, you haven't actually drawn the thing you think you drew. So you need to make sure you're keeping track of that. So the other situation is we did this process in the previous video, and we got to the end, and the last step in our process was check to make sure that all of your valence shells are filled for all of your atoms. And in the examples we did yesterday, the answer was yes. But sometimes the answer is no. And so we're going to look at what do we do when the answer is no. If we get to that point in the process and we haven't filled all of our valence shells, what we need to do is create multiple bonds between atoms. So sometimes, in order to fill all of the valence shells, we need to increase the amount of electrons that are being shared between atoms. So we need to increase the number of bonding electrons specifically. So we can do that by forming more than one bond between a pair of atoms. So everything that we looked at yesterday only had what we refer to as single bonds, meaning that there is only one pair of electrons being shared between those two atoms. But we can do more than that. We can form more than one bond between two atoms. So what we looked at yesterday, we refer to as a single bond, is one shared pair of electrons. We can also create double bonds, which are two shared pairs of electrons, or triple bonds, which are 3 shared pairs of electrons. And that is pretty much where it maxes out. Triple is the highest that you're going to see for the purposes of this course. There have been some very few recorded instances of higher sharing, higher bonding orders, but they are rare and they are weird. So single, double, triple are the ones that you encounter, generally speaking, in everyday life. So in these types of bonds, there are essentially 2 different ways that the bonds can actually form. These are referred to as sigma bonds and pi bonds. So I've mentioned at some point previously that when bonds form is when orbitals are overlapping. So sigma bonds are a direct overlap of orbitals between bonding nuclei. So if we imagine a nucleus here and a nucleus here, there might be an orbital pointing here and an orbital pointing here, and this little region of overlap in between is what we actually are referring to when we refer to a bond in general, specifically a sigma bond. So sigma bonds are the stronger of the 2 types. All single bonds are sigma bonds for that reason. And double and triple bonds always contain 1 sigma bond, and then any additional bonds are the other type, which are known as pi bonds. Pi bonds are a sort of sideways overlap. They're a little bit weird. So it's a sort of sideways overlap of orbitals, so they're not pointing directly at each other. If we have 1 nucleus here and 1 nucleus here with some kind of orbital, p orbital generally going this way, these orbitals we think of as looking like this sort of straight dumbbell shape. I'm actually going to move these a little bit closer together. The pi bond is sort of this weird sideways overlap that is a little bit hard to depict when thinking in terms of the standard shapes that we're used to looking at. But when these orbitals get close together, they actually kind of bend in towards each other. They warp a little bit. That allows them to have this slight overlap. And because it's kind of weird and kind of sideways and very small is why pi bonds are generally weaker than sigma bonds. Since we don't really get a ton of overlap between our orbitals. So this is why if something is only connected by 1 bond, it's going to be a sigma bond, because a pi bond by itself just isn't strong enough to actually hold 2 atoms together. So double bonds are always 1 sigma and 1 pi, and triple bonds are always 1 sigma and 2 pi. We can't have multiple sigma bonds between the same two atoms because two bonds can't occupy the same region of space. The sigma bond lies right between the two nuclei. There's only one path directly between the two nuclei, so you can't have two pairs of electrons occupying that same region of space. So they have to go kind of outside that direct path, which is why we get pi bonding. So this is how multiple bonds can occur, that we have these two different types of bonds that play together. As we add more bonds, as we go from a single bond to a double bond to a triple bond, it does get harder to break that bond. The bonds get stronger, but because of this difference between sigma and pi bonding, it's not a direct scaling. Like a double bond is not quite twice as strong as a single bond, because you've got this sigma bond as a single, but you're adding something weaker onto it to make it a double. So it doesn't double the strength when you double the amount of sharing, but it does increase it a good bit. So I think all of this will make more sense when we see it in action. So let's look at some examples for how we actually use this. So we have our same process for drawing Lewis structures that we worked on in the previous video. So we are going to take a look at this example first. So why don't you pause here, try this one on your own, getting up to this point. You should find, just based on what we did yesterday, that not all of your valence shells are filled, and then we will fix it together. So our first step is going to be figuring out our number of valence electrons. So hydrogen is in group 1, so that is going to bring 1 electron. Carbon is in group 4. Oxygen is in group 6. And there are 2 of those. And then don't forget about this negative charge is going to add 1 extra electron. So altogether, this gives us a total of 6 times 2 is 12, plus 4 is 16, 17, 18 electrons that we are going to need to represent in our structure. Now we need to figure out what is going to be the central atom. We have 2 unique atoms here. We have hydrogen and carbon, but hydrogen can never be a central atom because it can't form more than 1 bond. So our central atom is going to be carbon. And now we can arrange things. So if we put carbon in the middle, 2 oxygens and a hydrogen connected to that. So at this point we have gotten up through step 3 in our process. Step 4 is to add lone pairs to our peripheral atoms until their valence shells are filled. Hydrogen is good as is. It has the 2 bonds, 2 electrons from this bond, that fill up its valence shell, and that is all it wants. But oxygen wants to get to a filled octet. So each of these oxygen atoms is going to need 3 lone pairs for 6 additional electrons to give it the total of 8 that it wants. It's got 2 from the bond that it's involved with, so it needs 6 more to get to 8, and then same with this guy down here. It has 2 electrons shared in the bond plus 6 more for a total of 8. So our next step is to add any remaining electrons as lone pairs on the central atom. So we want to check and see, do we have any left that we can add to our central atom? We have 2, 4, 6 bonding electrons in our structure. 6 bonding electrons. And we have 2, 4, 6, 8, 10, 12 non-bonding electrons. So that gives us a total of 18, which is our target number. So we can't add any more. We don't have, here we go. We don't have any electrons left to add to our central atom, so this step is not applicable in this structure. So that brings us to the end here, where we want to check and make sure that all of our valence shells are filled. So looking at our various atoms, this hydrogen has access to the 2 electrons in that bond. 2 electrons is all that hydrogen wants, so that one is good. The oxygen atoms have their 3 lone pairs plus the bonding pair for a total of 8, which is good. The carbon has access to the electrons in these 3 bonds, and that's all. So the carbon only has 6 valence electrons as we have this structure drawn currently, not the 8 that it's looking for. So this is where we need to add this new step into our process where we can create multiple bonds. So we don't have any additional electrons to add. We cannot just add a lone pair onto the carbon here. But what we can do is create a double bond by increasing the number of electrons that are being shared. That's going to fill the valence shells of multiple atoms at once with those electrons, so that is going to help us out here. So what we can do is take a pair of electrons that were non-bonding electrons on a peripheral atom and use those to create a double bond from that peripheral atom to your central atom. And now if we check again, we find that this carbon now has a total of 8 valence electrons accessible to it. It's involved in 4 bonds, 2 singles and a double, for a total of 8 electrons. So we've fixed that problem. We didn't change anything about this oxygen at all, so it's still happy. We didn't change anything about this hydrogen, so it's still happy. We did change something about the way the electrons are arranged on this oxygen. Previously, it had 6 non-bonding electrons. My iPad screen is lagging. There we go. It had 6 non-bonding electrons and 2 bonding electrons for a total of 8. Now it has 4 non-bonding and 4 bonding, still a total of 8. So we've now kept the valence shell filled for the oxygen, and we've also now filled up the valence shell for the carbon as well by creating this second bond.